And that brings us over to the next topic, which is the definition of the black oil PVT properties. And black oil PVT properties, the simplest case that most of us learn about in university, is how can we actually calculate these different in-place volumes, or the so-called reserves. Reserves is something that's important for everybody. Managers and CEOs knows about it, geologists knows about it, petrophysicists knows about it, petroleum engineers knows about it. So it's easy to relate to, and it very quickly shows us the importance of a formation volume factor. And here we see the famous BO, or the BOI, that is required for us to actually calculate the original oil in place, which is always has the units of stock tank barrels, surface volumes. The same goes for gas. So to calculate the original oil in place, and note that we also here have a subscript O, and that's to essentially note that we have, this is the original oil in place originating from the reservoir oil. And to calculate that, as we learned many times in university, we simply need to know the oil volume down in the reservoir. So we account for water saturation, porosity, and the simple volumetrics, and then we divide by this formation volume factor. For calculating original gas in place, because there's no gas in the reservoir, at least before you produce, and this reservoir drops below the saturation pressure. So all the gas that you are essentially producing, or that you can calculate from a get-go perspective, is the gas that is in solution with the oil, and that is calculated simply by taking this original oil in place number and multiplying with the solution GOR. And just to remind ourselves what these different properties are defined as, it's always good to start with the formation volume factor, so the BO, which a lot of us is very familiar with, and it's defined as the reservoir volume, so that's of reservoir oil, divided by the surface volume originating from the reservoir oil. So super clear definition of that. And here we see a typical formation volume factor curve, where we plot oil formation volume factor versus pressure, and we differentiate between two parts of that in the PVT table. The first one is called essentially the saturated part, and when we're above the bubble point, so this is the bubble point indicating the bubble point, we're in what we call the undersaturated part of the black oil table. So all these points on these lines are representing essentially formation volume factors versus pressure, and we can see how that changes both below and above the saturation pressure. Similarly, for a solution GOR, we know that also that the strict definition of solution GOR is that we have the surface volume of gas originating from the reservoir oil divided by the surface volume, the volume of oil originating from the reservoir oil. And again, the people who have seen these curves many times, like myself, we know that the solution GOR is constant when we are above the saturation pressure, above the bubble point, in what we call the undersaturated range, pressure range. And when we go below the saturation pressure, sorry about that, below the saturation pressure, gas is coming out of solution, and the solution GOR of the oil that's remaining is going down. Okay? So then we'll get, at this particular pressure stage right here in the reservoir, oil has come out of solution, and we have a free gas phase in the reservoir, and we're building up gas saturation, and oil saturation is going down. Good. Now, when it become a little bit interesting is when we're going to talk about gas reservoirs when it comes to in-place numbers. Similarly, as in the case of the oil reservoir, we use this formation volume factor for gas, which is always this dry formation volume factor for gas, and there will be an exercise about the difference between the dry and the so-called wet formation volume factor. But important to note is that similarly as with oil, we simply take the reservoir volume of gas and we divide by the Bgd, and we can calculate the original gas in place. And if we would like to calculate how much condensate there is in place in that reservoir gas volume, we simply take the so-called solution CGR, indicated by this little rs right here, and multiply with the original with this original gas in place volume originating from the reservoir gas, and we get a original oil in place number with a subscript G, indicating that this oil originates from the reservoir gas. So if you are in a two-phase reservoir, you'll then have a oil in place calculated from the reservoir oil and an oil in place calculated from the reservoir gas, which we typically denote as condensate. That's why these subscripts are very, very important and very, very useful, and it helps us as engineers. When it comes to the definition of a gas formation volume factor, the strict definition of that is the reservoir gas volume divided by the surface volume of gas originating from the reservoir gas. And we denote that as Bgd. And the reason why we use Bgd is to differentiate between Bgd and this Bgw, which is called the wet gas formation volume factor. As we see on the plot right here, the definition of gas formation volume factor, Bgd, essentially provides us with a very not user-friendly plot versus pressure. And the reason is that you see that these values at very, very high conditions, and the high conditions is typically where this is important for us. They don't change that much compared to how much these values change at lower pressure. So you get a more or less unusable plot, and that's why when we actually plot gas formation volume factor, we actually typically plot the inverse of gas formation volume factor, which is called the gas expansion factor, which is the so-called small bg. And I see there's an error up here. It should be a small bg or 1 over the large bgd. And again, this is just the inverse. So for in a very simple world, the world that I live in, with ratios and fractions, etc., you just flip the equation you had on the other side, and it's defined as the surface volume of gas originating from the reservoir gas phase divided by the reservoir gas phase volume. And again, we also here differentiate between the saturated and undersaturated part of that particular curve. Similarly, we have the so-called solution CGR, which is at least above the saturation pressure, which is the so-called dew point constant, just as the solution GOR is constant. So we see in this particular scenario, we have a undersaturated region where the solution OGR or solution CGR, this particular PVT property has so many different names, but yeah, for the purposes of this, we call it either solution OGR or solution CGR, but it can also be vaporized oil ratio, for instance. And in many industry simulators, instead of using this little rs, which is the SPE nomenclature standard, you will see this large R subscript V, and V stands for vaporized. And you'll see that in Eclipse, you'll see that in Harmony, you'll see that in ResFrac, etc. But the definition of this RV or this little rs is the volume of surface oil originating from the reservoir gas divided by the surface volume of gas divided originating from the reservoir gas phase. And below the saturation pressure, similarly as what happens in the case of the solution GOR, this curve is dropping, but then it actually turns and becomes non-monotonic. So it actually goes up at low pressures. And that's a signature that's true in general for solution CGRs. And the reasons of why this is happening is beyond the scope of this particular short course. But I'll recommend you to go and visit one of our advanced classes. That'll explain you why this typical characteristic is true in general and why it's true for gas condensate reservoirs.